Good morning, students. In this class, we will see about Debye's model of specific heat capacity. This is also we already studied in solid state physics. In the last class, we saw Einstein's model of specific heat capacity. According to Einstein's assumptions, it is a quantum mechanical approach, and in that approach all the atoms are vibrate with same frequency but independent of each other. But what the problem was then, when Einstein calculated the specific heat capacity at low temperature, it will rise and it suddenly fell down during the low temperature. The reason for that is, what happened is, when it reaches the low temperature, the degrees of freedom will be freeze out. Normally, when there is a motion takes place, the term degrees of freedom will come. You all know what do you mean by degrees of freedom. Degrees of freedom is nothing but what are the possible ways the gas or that molecule will move. So, the degrees of freedom will freeze out when the gas or that molecule or that atom reaches the low temperature. Hence, suddenly the specific heat capacity was fell down. In order to overcome this, Debye considered the vibrational modes of the crystal as a whole. In that case, in Einstein's theory, it is considered as an individual, but here the vibrational modes of the crystals are considered as a whole. Hence, Debye suggested that it is possible to propagate waves through solids covering a wavelength region extending from low frequency up to short waves. This happens in the sound waves to infrared region. Sound waves to infrared region. Hence, Debye viewed the crystal as a continuous medium in which elastic waves propagate. Okay, so this is the difference between Einstein's model and Debye's model. So in Einstein's model, all the atoms are vibrate with the same frequency but independent of each other. Here, its vibration is not independent. The whole crystal vibration will be taken into consideration. Okay, so what happens? The frequency ranges from short waves, from low frequency up to short waves, which happens in the sound waves. Here we will find out what will be the Debye's cutoff frequency. What is Debye cutoff frequency? So Debye assumed this continuum model for all possible vibrational modes of the crystal. However, the total number of vibrations is restricted to 3n as in Einstein's model, where n is the total number of atoms. Thus, the frequency spectrum corresponding to perfect continuum is cut off in order to comply with a total of 3n modes. That is, the maximum frequency is called Debye's cutoff frequency, which is common for both longitudinal and transverse modes. We already know what is longitudinal mode and what is transverse mode. Therefore, the maximum frequency occurred is called as Debye cutoff frequency, and it is represented by the letter mu suffix d. It is represented by the letter mu suffix d, which is common for both longitudinal as well as transverse modes. Now, what will be the formula to find out mu d? Here you see mu of dv, that should be is equal to 4 pi v 1 by, not here 1 by, I think it is 2 by, you just change the notes, 2 by ct cube and 1 by cl cube. Okay, 2 by ct cube plus 1 by cl cube, where ct is the velocity during transverse vibration, cl is the vibration, cl is the velocity during longitudinal vibration. So this is the frequency, total frequency during that vibration, that is both common for transverse and longitudinal. Therefore 4 pi v, v is the volume, mu is the frequency. Therefore formula will be 4 pi v 2 by ct cube plus 1 by cl cube mu square dv. We already know the upper limit will be mu d. It is the maximum value called as Debye's frequency, cutoff frequency. Therefore the value ranges, integration ranges from 0 to mu d, z of mu d mu, that should be is equal to 4 pi v. You just change it, this is 2 by ct, this is correct, which is equal to 3n, which is equal to 3n. Then 4 pi v, this is 2 by ct cube and this is 1 by cl cube into 0 to mu d, mu square d mu, that is equal to 3n. Here mu square is nothing but mu cube by 3, upper limit minus lower limit, then it will come this term 4 pi v 2 by ct cube plus 1 by cl cube mu d cube 3 equal to 3n. Or to find out mu d cube, that is equal to, when you cross multiply it and we have taken the value 9n divided by 4 pi v 2 by ct cube plus 1 by cl cube whole power minus 1. In the Debye model, due to continuum mode of longitudinal and transverse velocities cl and ct are treated independent of wavelength. However, this is the limitation of this model, which makes it deviate from the experimental observation of specific heat. When you calculated the specific heat with respect to experimental methods, it will be deferred because this CL vibration and CT, that is the velocity of CL and the velocity due to transverse, are treated as independent of wavelength, Hence, the limitation will create in the findings of specific capacity by experimental observations. Okay, so this is Debye's cutoff frequency calculation. You just calculate, or you just remember the value of mu d. Mu d cube is equal to 9n by 4 pi v 2 by ct cube plus 1 by cl cube whole power minus 1. Okay. Now, how we calculate specific capacity according to Debye's theory? We know, according to Planck's expression for average energy of a harmonic oscillator, when multiplied by the total allowed modes of vibration gives the vibrational energy of the crystal. We already studied in the Einstein's theory also. Therefore, E is equal to h nu divided by e power h nu by kT minus 1 into integral 0 to mu d z of mu d mu. Substitute the value z of mu d mu here. This is in this equation. Then you will get, this is ct cube. We just change it. Okay. This is 1 by cl cube. So this equation changes like this. Then substitute the value here for x and xm. H nu by kt, h nu d by kt, which is represented as xm in the above equation. Then it becomes E is equal to 9n kt by h nu d the whole cube into kt integral 0 to x sum x cube divided by e power x minus 1 into dx. Okay. Now here one temperature called Debye's temperature is introduced as in Einstein's temperature. Here theta d, there we substituted theta e, here we are substituting theta d. Therefore E is equal to kt or E is equal to k into theta d. Equating these two equations, we know E equal to h nu. Therefore E is equal to k theta d or that is equal to h nu d. From this you can find out nu d, theta d is equal to h nu d by k. We are using this equation further. Okay, theta d is equal to h nu d by k. Theta d equal to h nu d by k. Therefore you find out rewriting this x sum in terms of theta d. X sum is equal to h nu d by k or nu d by k. Okay, x sum can be written as theta d by k. So use all these equations here. E is equal to 9n kt by h nu d the whole cube integral 0 to x sum x cube by e power x minus 1 into dx. Substitute instead of x sum here at very low temperature. At a high temperature, what happens? At very high temperature, T is very much greater than theta d. Hence, x is very small. Therefore, e power x can be reduced to 1 plus x. Okay? When T is very much greater than theta d, x is small. When x is small, e power x is also very small. Therefore, it is reduced as 1 plus x. Now, substitute this value. E is equal to 9n t by theta d the whole cube integral 0 to theta d by t. That is x sum. Instead of x sum, you are putting this value x square dx. When you simplify it, you will get 3n kt. But we know nk is nothing but r. Therefore, 3rt. Here, the above equation, theta d is equal to h nu d by k, xm is equal to theta d by t, and nk is equal to r. Therefore, we already found out the value of, that is the energy. Differentiating this energy with respect to temperature, we will get the specific capacity, we know already. Therefore, Cv is equal to dou E by 2T, that is equal to dou by dou T of 3RT, that is equal to 3R. This 3R is nothing but what? As told in Dulong and Petit's law. Similarly, as in Einstein's model, the results are same. Okay? So, at high temperature, Debye model of specific capacity gives the same result as in the Einstein's model as well as in the classical Dulong and Petit's law model. Okay? Clear. Now, what happens at very low temperature? Here, T is very much lesser than theta d. The temperature will be lesser than the cutoff frequency. Then, the upper limit changed to infinity. Upper limit changed to infinity. The integral part of the equation becomes integral 0 to infinity x cube dx divided by e power x minus 1, whose value will be 5 by 4 by 50. When you solve it by integration by parts, then you will get the result 5 by 5 power 4 by 50. Therefore, substitute in the above equation, you will get E is equal to 9n kt by h nu d the whole cube. Instead of that x cube dx by e power x minus 1 integral 0 to infinity, you substitute 5 power 4 by 50. When you solve it, you will get this equation. This will be what? The energy at very low temperature. When you are differentiating these things, you will get C. Therefore, C is equal to dou u by dou t, dou e by dou t, that is equal to dou by dou t of this thing. When you solve it, what will be CV value? This is the CV value. CV, that is equal to 12 by 5, 5 power 4, nk T by theta d the whole cube. Hence, this specific heat capacity is mainly depends upon this T cube value only. Hence, this law is called as Debye's T cube law. Debye's T cube law. This law is satisfied in the range T less than theta d by 10. So, at low temperature, this law satisfies only up to the temperature T less than theta d by 10. After that, when the low temperature goes on, then the value will not give, the Debye's theory will not work. So this is the limitation of Debye's theory. So Debye's theory works up to T less than theta d by 10. If the low temperature goes beyond that, then this Debye's theory doesn't work. So this is the limitation of Debye's theory. Debye's theory is otherwise called as Debye's T cube law. That is, the specific capacity is directly proportional to the value of T cube. Okay. So this is Debye's specific capacity model. Okay. So in the last class we saw Einstein's model. In this class we studied Debye's model. Okay. Of specific capacity. In both these questions, any one question is coming for the exams, so you just prepare it, and when you solve it, it is very easy. Just when you are seeing this in the screen, it may be somewhat confusion. Otherwise, when you study with material and my lecture, then it will be very easy. So you all will practice it in your home and study. Okay. So in the next class, we will come with another topic. Okay. Thank you. Have a nice day.